Hi, myself Prajal Makkar, and in this video, I'll provide my demonstration for the SIT 221 task 8.1p on graph algorithms. I'll cover the key ideas, algorithms, and answers for each question in this video. Part 1 was finding hotel with the maximum number of shortest paths available. Miss Marple wanted to find maximum number of shortest paths from the train station, and the in this answer I use the method BFS, which is breadth first search, which found the shortest number of paths in unweighted graphs by exploring neighbors level by level. In this, the key was to track both the shortest distance and count the number of shortest paths from each nodes. The algorithm used was easy. I initialized the distance with infinity, count with 0, and I set the starting distance to 0, and the count started at 1. When BFS was executed the first time, the distance was updated as well as the count, and it would just add the count if the shortest path was found. This ran till O n plus m times, n being the number of nodes and m being the number of edges. Part B, this was a testing connectivity of the network. When executing BFS from any node, if after BFS all nodes were visited, the graph is still connected, otherwise it's disconnected. If all nodes were visited, that meant the graph was connected. This also ran till the O n plus m number of times, as I have written in my complexity right here. Then the part C was runtime of the DFS using adjacency matrix. In this, the runtime was O n square, as checking neighbors required scanning every node for each of the n nodes. And then the part D, the graph one. In this, the cost of the adjacency matrix, I ran Dijkstra's algorithm from node 1 to find the shortest number of paths available. This used a priority queue to pick the shortest, closest unvisited node, updating distance of to the neighbors each time the older nodes are removed from the queue corresponding when the shortest path is finalized. This produced the shortest path tree from node 1. This was the part D. And then the last question, if all just a moment, let me move my video. Yeah. Increasing all edge weights by 1. If all edge weights by increased by 1, the shortest path will change. Paths with more edges get penalized more, which can cause a previously longer path to become shorter or vice versa. This was my part E, and this completes my demonstration for the task 8.1, and that's a summary of my solutions for the graph algorithm in this task. Thank you for watching.